All right, today we're diving into something truly fascinating. It's the spot where cutting-edge engineering meets artificial intelligence. We're going to explore how AI is learning to predict the exact moment when the very materials we build our world on are about to fail.
You know, it really all starts with a simple, almost childlike question. Why do things break? And I'm not talking about a big, sudden impact. I mean, over time, after being used again and again and again. Why is it that solid materials seem to just get tired and then suddenly give way?
Well, that question leads us straight into what engineers call the breaking point problem. Now, this isn't some new puzzle. It's a challenge that has defined the limits of safety and innovation for centuries. But now we're starting to look at it in a powerful new light.
The technical term for this whole process is material fatigue. It's this slow, kind of creeping process where every single applied load, think about an airplane's wing flexing in turbulence, causes these tiny microscopic bits of damage. Over thousands or even millions of those cycles, that damage builds up until the material just can't hang on anymore.
And this is not just some academic concept, believe me. Material fatigue is the hidden culprit behind some of the most catastrophic failures you can imagine. We're talking about an airplane part failing mid-flight, a bridge collapsing, or a critical machine just giving out with zero warning. The stakes really couldn't be any higher.
For a long time, we've had rules and methods we thought could predict this. But here's the thing. As our engineering gets more and more complex, those old rules are really starting to show their cracks.
See, our traditional methods were mostly developed in a lab, under these perfect, ideal conditions with simple, predictable cycles of stress. But the real world? Oh, it's messy. It's got constantly changing loads, hidden stresses from the manufacturing process, and all sorts of environmental factors that can completely change how a material behaves.
And here's the crucial point. These old models just can't account for all that real-world complexity. They miss stuff like the order in which loads are applied, or how a material's internal stress can kind of relax over time, or how its properties might get stronger in one direction but not another, and they especially struggle with those invisible stresses left over from things like welding.
So this is where the story takes a really exciting turn. To handle all the complexity that our traditional formulas just can't, we found a brand new tool, artificial intelligence.
And what's interesting is that for years, the problem hasn't been a lack of data. We have collected enormous, just mountains of data from sensors, from simulations, from experiments. So no, the data is not the problem.
The real challenge has always been our inability to see the subtle, interconnected patterns that are hidden deep inside all that data. The relationships between dozens of variables are just too complex, too nonlinear for a simple equation to capture. But you know what? This is exactly what AI models are built for.
So how does this actually work in practice? Well, it's not just one single magic algorithm. It's more like a whole suite of different AI techniques being applied to very specific problems.
And the versatility of these techniques is honestly pretty impressive. You've got researchers using artificial neural networks to model the incredibly complex ways that polymers stretch. Or they're using something called Gaussian process regression to pinpoint the exact location on a welded joint where a failure is most likely to begin. It's even being used in civil engineering to understand how soil behaves during an earthquake.
And the result of all this? A dramatic, massive leap in performance. Study after study shows that these AI-driven models are significantly more accurate at predicting material failure than the classical methods. By recognizing those complex, messy patterns in the data, they can handle way more variables and give us a much clearer picture of a material's future.
This is so much more than just a minor improvement. It's really a fundamental shift in how we approach engineering, safety, and design. It's paving the way for a much smarter and way more resilient future.
Just think about it for a second. Being able to predict failure with high accuracy has these enormous knock-on benefits. We get safer bridges and airplanes, more reliable products that don't break on us, and we give engineers the freedom to innovate with new materials and new designs, because they can be confident that they know exactly where the limits are. And that brings us to a final, kind of provocative thought. Right now, AI is helping us predict the breaking point. But as it gets better and better, if we can achieve near-perfect prediction of failure, does that mean we can finally start to design things that never fail at all? It's something to think about. Thanks for tuning in.